Okay, so in this video we move into the second half of our Surds and Indices topic, and that is we have a look at indices. So this first video should really be very much a review of index laws with which you are already familiar. So some terminology and some notation. A power is a product of a certain number of factors. So for example, 5 cubed is a power, the whole thing is a power. And it is the product of 3 5s. Okay, it means that we do 5 times 5 times 5. That is, we multiply, hence the word product, 5 3 times. Okay, so it's nothing to do with 5 times 3. It's 5 times itself 3 times. Okay, it's really important that you're clear on that difference. So for example, a to the power of n means a times a times a times a times a n times. Okay, when we talk about a to the power of n, the whole thing is called a power. A is the base of the power, okay, and n is the index or the exponent. Okay, we often talk about something being to the power of something else, and we talk about therefore the index or the exponent being the power. It's not actually technically correct, but it is commonly understood when you say that. So index or exponent. Obviously the plural of the word index is indices. So one index, more than one indices. Multiple indices. When we work with expressions involving indices, it's really important that you understand their place in the order of operations. And so you would have learnt your order of operations perhaps as BODMAS or BIDMAS or BOMDAS or BIMDAS, or in America they learn PEMDAS because they talk about parentheses rather than brackets, and they use E as exponent here at this step. The key thing is that this is where the powers happen, okay? And the old BODMAS, the letter O actually stands for order, okay? 2 to the order of 5 is the same as 2 to the power of 5. But that's quite an old-fashioned kind of language, and in fact, a lot of primary school teachers who still teach BODMAS tend to teach the O as being of, but it's not of, it's order, it's powers, it's indices, it's exponents, okay? So they happen after brackets. So the key thing is, if you write, 2x squared, it means that you square the x and then you multiply it by 2, which means that if you have 2 times 3 squared, that's not 6 squared. It's 3 squared and then multiplied by 2. The powers happen before the multiplication. Okay, it's a similar issue with the negatives. A common error is negative x squared. Okay, so for example, negative 2 squared is negative 4. It's not positive 4. Negative 2 all squared means negative 2 times negative 2, and so that's positive 4. But negative 2 squared is negative 1 times 2 squared. The power happens before the multiplication. So it's 4, 2 squared is 4, and then multiply by negative 1. Okay, let's have a look at reviewing the index laws with which we should be familiar. So if we are multiplying two powers with the same base, so a to the power of m multiplied by a to the power of n. So for example, let's have a talk about this one before we come up with our generalized index law. So if we were to have x squared times x to the power of 4, okay? Now x squared means x times x, okay? And then we are doing that multiplied by x to the power of 4. Let's use a different colour there. X to the power of 4. Now x to the power of 4 is x times x times x times x. Okay. So within a power, we're doing multiplication, which means that if we are multiplying two powers together, it's all multiplication. Okay. X squared means we're doing x times x, x multiplying by itself 2 times, and then we're multiplying that by x 4 times. So in total, we're ending up with 6 x's, okay? And that would be, if we generalize that, if we have m lots of a, well not m lots of a multiplied by itself m times, and then we multiply that by another n lots of a, or a multiplied by itself n times, we're going to end up with a total of m plus n products of a. Okay, so a times a times a, m plus n times. Okay, so generally speaking, our index law, when we're multiplying powers with the same base, we add together, the exponents. It's a to the power of m plus n. Okay, when we're dividing, So let's look at our illustration here in this column first. So if we've got u to the power of 5, that's u times u times u times u times u, 5 times, over u to the power of 3, u times u times u. Oops. Okay, so we know we can simplify fractions by dividing, well, we can multiply, but in this case we want to simplify by dividing the numerator and denominator by the same thing. So if we divide the numerator and denominator by u, okay, we're going to end up with one of those u's on each of the numerator and denominator cancels down to be 1 over 1. If we divide by u again, u divided by u is 1, u divided by u is 1. If we divide by u again, u divided by u is 1, u divided by u is 1. And actually now we've got no more u's that we could cancel down with on the denominator, so we're just left with u times u on the numerator, which is u squared, over 1 on the denominator, and so we just have u squared. And so u to the power of 5 divided by u to the power of 3, all of those u's on the denominator cancel, each of them cancels out a u on the numerator. And so the easier way to do that efficiently is to recognize that if we have a to the power of m, so a multiplied by itself m times, divided by a multiplied by itself n times, the n a's on the denominator will be subtracted from the m a's on the numerator. So we're going to get a to the power of m minus n when we are dividing powers. Importantly, they have to have the same base. If that was u to the power of 5 over x cubed, there's nothing common in the numerator and denominator, and nothing is going to cancel down. So these index laws are all dealing with the same base. Now, if we have a to the power of 0, okay, so let's have a think about a separate example first. So let's follow on from this division example, and let's think about if this was u to the power of 5 divided by u to the power of 5. Okay, so that's u times u times u. In fact, let me make it 3 just so it's a bit quicker. U to the power of 3 divided by u to the power of 3. That's u times u on the numerator over u times u on the denominator. And we know from simplifying our fractions, we can divide top and bottom by u, divide top and bottom by u, and divide top and bottom by u, and we just have 1 over 1 left, which is just 1. And that makes sense, because anything divided by itself is 1. However, if we were to think about this using our index laws for dividing when we have the same base, this is u to the power of 3 minus 3, which is u to the power of 0. And so what we see is by considering this same problem in two different ways, we get u to the power of 0 one way, and we get 1 the other way. And so therefore, those two things must be equal to each other. Okay, and therefore u to the power of 0 is 1. Okay, so a to the power of 0 is 1. Y to the power of 0 is therefore 1. Where we need to be a bit careful is if we had 2y to the power of 0. So that's 2 times. Remember the order of operations. The power of 0 happens first. It's different to this. These aren't the same thing. Okay, so this means 2 times y to the power of 0, which means 2 times 1, and so that's just 2. Whereas this one means 2y all to the power of 0, and so that will just be 1. Okay, so again, that order of operations distinction is important. Okay, if we have one power after another, so we've got a to the power of m and then to the power of n. So let's think about that with this example. So if we have z squared and then all of that cubed, essentially we have z squared being cubed. So z squared times z squared times z squared. Okay, which means we can either use our index laws for multiplying. We can add 2 plus 2 plus 2. Essentially we have 3 lots of 2. And so it's z to the power of 3 lots of 2, which is 6. Okay, so same logic here. This is a to the power of n lots of m. So we can multiply those powers together when we're applying one power after another. Okay, and then finally, if we are multiplying two things together all to the same power, now because powers essentially are multiplication, okay, they're not the same, but there's multiplication is the operation inherent in a power, the power of a product can very easily be expanded. So for example, if we've got 3x all to the power of 4, that means 3x times 3x times 3x times 3x. Now remember, 3x is 3 times x, so everything there is multiplication. 3 times x times 3 times x times 3 times x times 3 times x. Now we know if we're multiplying lots of things together, the order that we multiply in doesn't matter. So we can think about this as being 3 times 3 times 3 times 3 times x times x times x times x. Yeah? So 3 times 3 times 3 times 3, we could write that as 3 to the power of 4 times x to the power of 4. Okay, so essentially if we have 3x all to the power of 4, we can just do 3 to the power of 4 times x to the power of 4. And obviously 3 to the power of 4, if we know our powers, is 81. It's really important that you work on, it'll be much easier for you in this topic if you work on knowing some of those basic powers, sort of 2 up to the power of about 6 off the top of your head. Although powers of 2 are very easily generated because it's just a doubling pattern. 2 to the power of 1, 2 to the power of 2, keep doubling, 8, 16, 32, 64, 128, 256, 512, 1024, etc. So this is 2 to the 1, this is 2 to the 2, 2 to the 3, 2 to the 4, 5, 6, 7, 8, 9, 10. So you should be able to generate powers of 2 really easily. Powers of 3, you should certainly know, up to 3 to the power of 4, probably. Powers of 4, again, maybe, 4 cubed, 5 up to 5 cubed, 6 cubed, 7 cubed. They should be numbers that you're familiar with. So perhaps draw yourself up a bit of a chart and just put that somewhere where you're going to see it frequently because you'll use them quite a lot. Okay, so we just realised that 3x all to the power of 4 is the same as 3 to the power of 4 times x to the power of 4, which tidies up to 81x to the 4, but we're more interested in the general rule. So if we have a times b to the power of n, we just have a to the power of n times b to the power of n. Same for division. Okay, if we have a over b all to the power of n, so let's have a look at this example, p over q all to the power of 5, well that's p over q times p over q times p over q times p over q times p over q, and we know when we are multiplying fractions, it's really just numerators p times p times p times p times p on the numerator over denominators q times q times q times q times q on the denominator. So essentially we just have here p to the power of 5 on the numerator and q to the power of 5 on the denominator, and so we can go straight there. So if it's multiplication or division in the brackets, then we can essentially just expand out the brackets, if you like, by applying the power to everything in the brackets. However, if it is addition or subtraction, okay, a plus b to the power of n does not equal a to the power of n plus b to the power of n. Okay, similarly, a minus b to the power of n does not equal a to the power of n minus b to the power of n. These are common issues that students have. Okay, it's as simple as, x plus 2 all squared. It's not x squared plus 4. It's a perfect square and expands out to x squared plus 4x plus 4. Okay, so you need to actually expand the brackets, and that's again because the brackets are overriding the power. You have to do addition or subtraction first, whereas here, yes, you have to do multiplication first, but actually because powers essentially are multiplication, when you actually write it all out, you see that it's all multiplication, and therefore we can sort of switch around the order of what's happening. Whereas a plus b to the power of, if you've got a plus b to the power of 5, that is a plus b times a plus b times a plus b, etc. Okay, 5 times, and you can't just, you only way around that is to expand it all out. Okay, similarly, if you have different bases, okay, there's nothing you can do about that. Different bases, there's nothing that you can do about that. If you are adding or subtracting things with the same base, there's also nothing we can do about that. So 2 to the power of 2 plus 2 to the power of 7, there's no index law for that. Okay, you just work out what 2 squared is and you work out what 2 to the power of 7 is and you add them together. So being clear about what you can do, but also what you can't do, okay? What there aren't index laws for. Okay, let's work through some examples. Express each of the following in simplest form. Okay, so we've got 2x cubed all to the power of 5. Now I'm going to write out all the steps here so I'm really clear about what index laws I'm using, but by all means, you should be able to do, you should not necessarily need to write down all of these steps. Okay, so here we have a power of a product of two things. So therefore, it's going to be 2 to the power of 5 times x cubed to the power of 5. And then here where we've got x cubed to the power of 5, we can make use of our index law, which says we multiply those two powers together. 2 to the power of 5 is 32. Again, learn some of your early powers if you need to, or start writing it out. 2 to the power of 1 2, all I'm doing is doubling. Okay, if I double 1, 2, well, you know, you start with 2 to the power of 0 is 1, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. So if you double 5 times from 1, you get to 32. Okay, so it's 2 to the power of 5 is 32, x cubed then to the power of 5, we multiply those powers together, so that's x to the power of 15. Okay, a cubed times a to the power of b. Alright, so we add powers together when they have the same base, so this is going to be a to the power of 3 plus b. Alright, example 3, we've got a fraction there, all to the power of 2. So let's focus on that first. We've got all multiplication and division in here, so we can simply just square everything that's going on in here. So let's see if we can do a bit of this in our head as we do it to make life a bit easier. Yes, we could simplify the fraction first. You can do things in different orders, and that's up to you, but I would encourage you to sort of develop a system so that you always kind of do things in the same order. I'm going to focus on expanding out any brackets first, then I'm going to worry about simplification by multiplying or dividing any powers with the same base. Okay, so let's just square everything first and get rid of that outside bracket. So 3 squared is 9, m squared and then squared again. We multiply those powers together. 2 times 2 is 4, so that's m to the power of 4. And then we've got n squared divided by, still got, we need to square. 9 squared is 81. And n to the power of 4 and then squared, we multiply those powers together. Okay, so it's going to be n to the power of 8. Alright, then we can focus on simplifying. So the 9 on 81, that's going to simplify down to 1 on 9. Okay, so I don't need to write 1 unless it's the only thing on the numerator. So I'm just going to have 9 on the denominator. The m to the power of 4 on the numerator, there's nothing for that to cancel down with. The n squared divided by n to the power of 8. Okay, we could subtract powers and have n to the power of -6. We'll talk about negative powers down the track, but actually what I'm just going to recognise is that the 2 n's on the numerator are going to cancel down with 2 of the 8 n's on the denominator, and so it's going to leave us with 6 n's on the denominator. So m to the power of 4 over 9n to the power of 6. Okay, example 4. We've got 3x to the power of 0 minus 3x all to the power of 0. So making a clear distinction about the difference between these two things. So 3x to the 0 means 3 times 1, whereas 3x all to the power of 0 means that that's 1. So we've got 3 minus 1, and so that's going to be equal to 2. Okay, example 5, we want to expand out these brackets first. So let's focus on raising everything to the power of 4. So we have 2 to the power of 4, which I know is 16. And p squared and then to the power of 4, so we multiply those powers together. So we get p to the power of 8. Multiplied by, let's expand out this one. So squaring everything, 3 squared is 9. Multiplied by p squared and then squared again. Adding those powers is p to the power of 4 and then q squared. Okay, now we can focus on multiplying. Everything is multiplication, so remember this is 16 times p to the 8 here as well. So we can do the multiplication in any order we want. Let's multiply the number parts together. Let's multiply the p parts together. Okay, so 16 times 9. Okay, well, you could do this a couple of different ways. You could do 10 times 9 plus 6 times 9, or you could do 16 times 10 is 160 and then take away 9. So we're going to have 150 it's 10 times 16 and then take away one lot of 16. That didn't add up. Or you do, as I said, you do 9 tens are 90 plus 6 nines are 54. So we're going to get 144, or 160 take away 16. Okay, p to the power of 8 times p to the power of 4, so multiplying things with the same basis, we add those powers, so that's p to the power of 8 plus 4, which is 12. And then just q squared. It's got nothing to go together with. Okay, example 6. So again, it's just about taking things one step at a time. I'm going to focus on the brackets first, then I'm going to focus on multiplying the two fractions together, and then I'm going to worry about simplifying by doing any division. Okay. Alright, so this is 3 cubed, which is 27. X squared and then cubed, multiplying 2 times 3 is x to the power of 6. I have y cubed over 2xy squared multiplied by 8x cubed y to the 4 over 9x to the 4y squared. Now, I could have simplified these fractions, but personally I always, as I said, have a system that works for you. I always expand out any brackets, multiply together any fractions, and then simplify after that. Okay, so 27, the only thing I might do some cancelling down with is the numbers though, just so I don't have to do 27 times 8 and then cancel it down later. I'm not going to do any cross cancelling. If you do too much cross cancelling, you'll find you have everything crossed out and you've got no idea of what's left. Okay, so try to be a bit minimal in the way you cancel. I'm just going to cancel down the numbers. I'm going to recognise 27 is 3 times 9, so that's going to cancel down, and I'm going to cancel down the 8 and the 2. Okay, so now I'm going to multiply across the numerator and across the denominator. So I'm going to have 3 times 4 on the numerator, so that's 12 for the number. And then we've got x to the 6 times x cubed, so adding those powers together, it's x to the power of 9. And then y cubed times y to the power of 4, so adding those powers together, it is 7. Over, let's have a look at the denominator. We've got 1 times 1 there, so no number. X times x to the power of 4. Now remember, x is x to the power of 1. Okay, so x to the power of 1 times x to the power of 4, I add those powers together and I get x to the power of 5. And then y squared times y squared, we add those powers together and we get y to the power of 4. Okay, if you want to write the 1 you can, but you really don't need to. Then we're just focusing on simplifying the numbers, the x parts and the y parts. Okay, so 12 divided by 1 is just 12. X to the power of 9 divided by x to the power of 5, subtracting the powers, 9 minus 5 is 4, so it's x to the power of 4. Y to the power of 7 divided by y to the power of 4, again subtracting powers, 7 minus 4 is 3. Okay, and question 7. Again, I'm going to focus on brackets first. I'm also going to focus on what it is to divide by a fraction. I know it's the same as multiplying by the reciprocal. Okay. So we'll deal with those two things first. So let's expand out this bracket at this first fraction. So we're going to have 2 squared, which is 4, x cubed and then squared, which is x to the power of 6, over 3 squared, which is 9. And I'm going to multiply by, and I'm going to flip this second fraction, 9 over 4x cubed. Okay, I might do some cross cancelling of the numbers. So I'm going to have 4 and 4 cancel down, and 9 and 9 cancel down, so that's all very neat. So on the numerator I've got 1 times x to the power of 6, on the denominator I've got 1 times x to the power of 3, and then I'm going to subtract my exponents because I'm dividing powers with the same base, so x to the 6 divided by x cubed is x to the power of 6 minus 3, which is x to the power of 3. Okay, in these examples we want to evaluate, so that means actually come up with a numerical answer, okay? A single numerical answer. Evaluate the following without using a calculator. Okay, so we want to do 5 times negative 3 to the power of 4. So there's no bracket here, so this isn't negative 3 all to the power of 4, so this won't be positive, it's still going to be negative. So it's going to be 5 times, now 3 to the power of 4 is 81, so negative 3 to the power of 4 is negative 81. Alright, so my answer is going to be negative. 5 80s are 400 and 5 1s are 5, so negative 405. Alright, question 9. Now we need to be really careful with mixed numbers because a mixed number means 1.5 means 1 plus a half. Okay, and we know that if there's addition here, we can't just do 1 cubed plus half cubed. Okay, so mixed numbers, as always, really, when we're anywhere beyond primary school, are our enemy, and the first thing I want to do is write 1.5 as an improper fraction. So 1.5 is the same as 3 on 2 cubed, and now I've only got division in there, no addition, and so I can focus on it is 3 cubed, which is 27, over 2 cubed, which is 8. Making sure your fraction's in simplest form, which it is. Okay, question 10, we've got 7 to the power of 10 over 49 to the power of 3. Now, I don't want to have to work, I don't know what 7 to the power of 10 is. I don't want to have to work it out. Even if I had a calculator, it's enormous. Okay? 49 cubed, similarly, is also enormous. Alright, so I don't want to have to deal with working that out. We want to be able to do this without a calculator. We don't need a calculator to do these questions. Okay, so 7 to the power of 10 over 49 to the power of 3. So actually what I recognise here is 49 is a power of 7. So let's just focus on leaving them as powers, but let's write everything with a base of 7. So let's leave the numerator as 7 to the power of 10. Now 49 is 7 squared, and we've got that cubed. Now, when we have one power after another like this, we know we multiply those together. So what we have here is 7 to the power of 10 still on the numerator, divided by 7 to the power of 6. Okay, so now we can subtract powers, and we can do 7 to the power of 10 minus 6, so it's 7 to the power of 4. Now, I don't know 7 to the power of 4 off the top of my head. I know that 7 cubed is 343, and so 7 to the power of 4 is going to be that times 7 again. Okay, so I might need to do a little bit of maths. I might need to do 343 times 7. I could do 300 times 7 plus 40 times 7 plus 3 times 7. It's a lot to carry in my head, so I'm just going to do the long multiplication. 7 3s are 21, 7 4s are 28, plus 2 is 30. 7 3s are 21, plus 3 is 24. Oops, 24. So 2401. Again, you could work out that 7 times 300, is 2100, 7 times 40 is 280, and 7 times 3 is 21, and you could add those together, which is essentially what the long multiplication is doing. So this is 2401. Okay, and then question 11 here, we've got 4 squared and then to the power of 5 times 4 times a quarter cubed and then cubed again. The key thing here is there's lots going on, but everything's got a base of 4. So let's just focus on leaving everything as powers and simplifying things until, then we can see what's going on. So 4 squared and then to the power of 5, that's 4 to the power of 10. Okay, multiplied by, let's just leave that 4, that's 4 to the power of 1. And then we've got times, now this is going to be 1 cubed over 4 cubed. Okay, so we're going to have 1 over 4 cubed, and then we're going to have all of that cubed. Alright, so we've got, let's put those two together. We've got 4 to the power of 10 times 4 to the power of 1, so it's 4 to the power of 11, multiplied by, now here again we're going to have 1 cubed, which is still 1, 4 cubed and then cubed again. We multiply those powers together, so that's 4 to the power of 9. So actually, we've got 4 to the power of 11 over 1 times 1 over 4 to the power of 9. So we've actually just got 4 to the power of 11 over 4 to the power of 9. And then we can subtract powers when we have the same base and we're dividing, so that's 4 squared, and so this whole thing tidies up really nicely to equal 16. Okay, some practice here for you to do from exercise 3E, just practicing these index laws which you should be familiar with from previous year's learning.